Right. So this is almost like Towers of Hanoi, right? Where we kind of have some rules about whether or not we're allowed to push something onto the top of the stack or not. Okay. So we notice the stack is empty. We're fine. So we go ahead and we push that plus sign onto the top of the stack. Okay. Then we get to the B, not an operator, add it to the output queue. Okay. So notice that this guy over here is a queue, right? This guy's a stack, this guy's a queue. So we're working with a couple of different data structures here. Okay, so we just move the B, which is going to be some number in our algorithm, over to the output queue. Then we get to the multiplication. Okay, now multiplication is more important than addition, right? And we can go down, they have a chart in here that kind of gives you the breakdown, but for us, we kind of, because I said you just had to make this work for plus, minus, times, divide. So this is pretty much general knowledge for us at this point that multiplication, division, more important than addition and subtraction. Okay, so this decision is relatively easy for us to make, right? Okay, so multiplication, more important than addition, so we can go ahead and add it on top. It's more important, so it's going to be, in terms of the operators that are going to get processed next, it should get processed before the plus sign should. Okay? So that's why we go ahead and allow it to push on top of the plus sign, because at the very end, we're going to end up popping this stuff off, anything that's left. And it's going to go on to the end, and then we can do this thing left to right. Okay? So we go ahead and we move the multiplication, where are we at here? Multiplication on top of the addition. We do nothing special. All right, then we get to the C. C just goes on to our output queue. So far, anything that's a number, we just keep shifting over to the output queue. Then we get to the subtraction. All right, now we can say we're going to try to put subtraction on top of multiplication, but that's not allowed. Multiplication is a higher priority operator. So what we're going to do is we're going to go ahead and pop multiplication off and put it into the end of our queue. Okay, so we get multiplication out of here, we put it onto the end of our queue. Now we're going to try to put addition on top of, or I'm sorry, subtraction on top of addition. And that's not allowed either. So as we start kind of translating this into the algorithm, we want to think about, we can only push this on top of things that are less than us. Okay, so addition and subtraction, they're equal. It's not less than. So with that, if you kind of think about your math rules, right? Addition and subtraction, because they're equal strength operators, we always do them left to right. Same thing with multiplication and division. Okay, but multiplication and division always happen before addition and subtraction. All right, so after we've moved the multiplication over here, so they kind of skip a picture here in the middle. So multiplication shifts up here. Now we're going to try to add the subtraction on top of the addition, and because subtraction is not greater than addition, this is not allowed. So we need to go ahead and pop addition off. So then we end up having multiplication and addition both tacked on to the end of our queue, which then frees us up to go ahead and add the subtraction. That makes sense? So what's our rule? What's our rule here? An operator can get pushed onto the top of our operator stack if it is greater than, if its power, its priority is greater than the guy currently at the top of the stack. Not greater than or equal to, greater. Okay. Important distinction. Make sense? All right. So we got we've popped the multiplication and addition off. We've gone ahead now and finally we're able to push the subtraction on. We took us 3 tries, but we got it on there. Okay. Then we go ahead and move the D over here to our output queue. And now we're out of input. So when we're out of input, what do? We clear our operator stack. So we just pop off the operator stack till we're out of operators. And now what we've effectively done is we've loaded up our output queue, and at the end of the day, what has it really done? It's reordered our input queue. Okay, it's converted into what's called reverse Polish notation, or a prefix notation. How many of you have ever heard reverse Polish? notation. So here's a historical quiz question. So how many of you have had a graphing calculator? Okay. And every one of them was a Texas Instruments? Casio? Okay. None of them was an HP. So way back, so it's like back when calculators were cool. That time existed, trust me. Okay, I used to write software on my. I had a Hewlett-Packard graphic calculator, and I would write software during our math classes on that thing because the class was boring. So I would just. That's what you should do. If you're not going to pay attention to class, you should be writing software. It's the official. So in any case, Hewlett-Packard calculators still exist today, but they're mainly in like the tax industry. All right, so the prefix notation, or it's called reverse Polish, is the way a Hewlett-Packard calculator works. It works with a stack. If you want to add 2 plus 3 together, you put 2, enter, 3, enter, plus enter, and then it adds them together. Okay, so it pushes the 2 onto the stack, pushes the 3 onto the stack. You put in an operator, it does that operator to the guys that are currently on the stack, pushing the result back onto the stack. Right, so kind of get you used to using stacks, even though you maybe don't think about them as stacks. But back then, if you had the Hewlett-Packard graphic calculators, you were one of the cool kids. Okay, it was like I'm trying to think what it was compared to. It was almost like Mac versus PC type thing, where the PC people actually thought you were cooler if you had a Mac, which is not really. That's different than today, right? Most PC folks, when they see somebody with a Mac, it's like, oh, you have a Mac, like oh, it's like almost like a toy computer, right? So that's your mentality, isn't it? Yeah. It's like that's a toy computer. And the Mac people are saying, you wish you could afford this. I haven't eaten in 8 months. All right, so, but yeah, back then it was. In fact, you could get these memory cards to expand the memory. I had an HP 48GX graphing calculator, which was that was the top of the line, and I expanded. I was at the University of Illinois, and I expanded the memory. I went into the bookstore there, and they had it out like it was like this really cool piece of equipment, like under glass and stuff like that. The 128 kilobyte expansion card for more memory. Sick. I want to see if we can. Can we find a HP 48GX? Oh yeah, look at that guy. Oh, that's a cool thing. Yeah, you had a little carrying case for it, with a zipper. Oh, yeah, that just looks way cooler than your Texas Instruments calculators. It's just garbage. But then I was introduced to the TI-92, which does symbolic algebra and calculus, right? How many of you have seen the TI-92, Texas Instruments? So TI-92, that's this guy, the tablet graphing calculator. Okay. Now the problem with this, and see, I mean, you could do really cool stuff with the TI-92. The problem with that is teachers knew, because that is definitely identifiable, right? I mean, that thing is, it's effectively like the thing for the Nintendo Wii U. Yeah. I don't know. I haven't felt the size of the Switch thing, but like the thing for the Wii U, the tablet part of it, it's like that. So your teacher definitely knew. Well, so then they came out with the TI-89, which was the TI-92 software on a calculator that looked just like the pedestrian Texas Instruments calculators. And then what would you do is you would get your answer. So if you were doing like integration or derivatives, you would type in the question and press enter. It would give you the answer. And then you would reverse engineer your work. Sick? So that's when I abandoned the Hewlett-Packards. I still have my HP calculator somewhere. I'm kind of sad thinking about these old memories. um, learned way more about the history of graphing calculators than we were talking about calculators. Where are we at here? This guy. All right, so now we were sitting here. We have one lab. We've cleared our input queue. Now we're going to go ahead and clear our operator stack. Just pop stuff off the stack till it's empty. Effectively getting everything out here into our output queue, ready to calculate. Okay, and then at that point, what do? We start doing our math off this guy. So when you think about the math, let's just go back up here and look at our original. If you're doing this with correct order of operation, the first math you should do here is actually this guy right here. Okay, the first math you should do here is the B times C, correct? Then after that, you do left to right. So you get the result of B times C, and you add that to A. And then you subtract from that D. So we come back down here. We'll go ahead, and when we're actually calculating this, we're going to use a stack to calculate. So we'll push A onto the stack. We'll push B onto the stack. We'll push C onto the stack. Then we hit an operator. That's the first operator we should do math with. So we'll pop B and C off the stack, multiply them together, pushing the result back on. Then we hit another operator. So that's our B times C. The first thing we actually do is B times C there. Then we push the result back onto the stack. So now we still have two numbers on the stack. We have A, and then on top of that, the result of B times C. Then we hit addition. So an operator says, pop two things off the stack, perform this operator to those two things. So we will pop off the result of B times C and pop off A, add them together, push the result back onto the stack. Okay? Then we get to the D, push that onto the stack. Then we get to the minus. Minus says, pop two things off the stack, perform the operator, push the result back onto the stack. We're done. Top of the stack is our answer. Okay? Now, where we do need to be a little careful is the order in which we do these operations. Okay? Because that very last time we had one number on the stack from all of this crap, right? And then we pushed on top of that D. And then we got to the minus. So we are subtracting D from the value that is already on the stack. Well, so when we pop the first value off the stack, we get the D. We pop the second value off the stack, we get the answer from all the previous math. We are taking that second pop minus the first pop. So we want to make sure we use the numbers in the correct order when we're actually doing the math. That makes sense? Once we get that answer, we push the result back onto the stack. Now our output queue is empty because we've been dequeuing stuff from it. We have our solution stack, if you will, sitting there. And because our output queue is empty, we know that our answer, our final answer following all the orders of operation correctly, left to not just left to right, but multiplication and division more important than addition and subtraction, we know that the top of the stack, either the peak or the pop, depending on whether you want to remove it or not, is the final answer of your math. That make sense? Okay, so any questions about how the shunting yard algorithm works at this point? Okay, so we completely understand what we're trying to do. Okay, now we actually have to be able to do it. Okay, those are two separate things. Okay, but I guarantee 100% of the time, if you don't know what you're trying to do, you will not be able to do it. Everybody can agree with me? Now, interesting follow-up question. How many of you tried to just do it before you completely understood what you were trying to do? I'm guessing half of you. You kind of see the importance of going through this exercise here, of making sure you understand in total what you're actually trying to accomplish before you start writing random Java code to solve a problem that you don't understand. Pretty important. Okay? You think programming is hard when you did know what you were trying to do. Way harder. Well, actually, maybe way easier. You won't even know if you're right or wrong. You just assume. I always like those the self-evaluations when students turn stuff in. It says, yeah, I don't know if this works. Couldn't figure out how to test it. Good. So let me get this straight. You couldn't figure out how to run your code. I have real low expectations in whether or not the random crap you put in there was right. All right. So let's go back here. So we are going to need a stack, right, for our operators. So we can go ahead and build a quick stack data structure. We don't want to use the built-in one. We might as well write our own because that's what the cool kids do, right? Obviously. How many of you use the built-in stack? Actually, have I taught the built-in stack yet? Oh, I have not. Maybe I should teach the built-in stack for this. Yeah, let's do that. You're lucky. All right, so let's do, because obviously inside of Java, we do have implementations of these various data structures, right? You got a linked list data structure. Have we talked about generics in here? I want to say we maybe did with array lists. The square bracket stuff, not square bracket, the angle bracket stuff, where you would say you want an array list capable of holding strings. You've seen that before? Okay, well, the same thing exists. That's something called generics in Java. Same thing exists for our different data structures. And actually, I want to say maybe stack doesn't exist, but linked list has push and pop. We'll find out here in a second. So inside of our, well, I'm going to go ahead and create an object for shunting yard. Okay, we'll have that guy kind of do all the stuff that we're going to do here and manipulate our various things. So let's go ahead here. New Java class. Okay, so we're going to have a shunting yard object. Yes, add that to my Git. Okay. So we know that with the shunting yard object, this guy's going to maintain a couple of different things, right? He's going to maintain a input queue. He's going to maintain a operator stack. He's going to maintain an output queue. And then ultimately, he's going to have a solution stack, something like that. All right. Well, we've already written our queue data structure that holds strings, correct? So we'll go ahead and use that guy as a starting point. Think about this. Yeah, we're okay with using stack. Yeah. The whole reason I was saying is, are we okay using a stack, built-in stack for doing our solution stack or operator stack? The answer is yes, because we know that those guys are going to hold a bunch of either strings or chars or something like that, and the solution stack will hold numbers. Okay, so shunting yard, we're going to go ahead and create our various queues and stacks. So we're going to have our input queue. Input queue. And actually, this guy is going to be a queue called input queue. Then we're going to have a private. Okay, so inside of java.util, notice here we have a class called stack. And you see how it has the little angle brackets with an E in the middle of it? That says we're allowed to, when we create it, say what kind of animal we plan on putting in there. Okay? Now, we can choose to have a stack of strings. We could also choose to have a stack of chars here. Either one would work. If we use chars, then we're going to have to get char at 0 from our strings because we know all of our operators are single character things. Let's just keep it as strings for right now. So I'm going to say this guy is going to be a stack of strings. And we're going to call this guy the op stack. Okay. Then we need our output queue, which is just going to be another one of our queues. And that guy's going to be also a string queue. And just to show you real quick, I believe, yep. So inside of java.util, we do have a queue built in. We could use that, or we can just use ours. Let's use ours, you know, for act of solidarity, right? So we'll go ahead and use ours. And we know that ours doesn't support generics, but ours is by default strings. That's how we wrote it. Okay, so we'll say private queue, output queue. All right, and then we know we're going to need a stack for our final answer. And if we want, we can go ahead and let's keep this as a stack of strings, because our stack object types do need to be our stack object that's built into Java does need to hold object types, which means we can't have a stack of ints. We could have a stack of integer objects that we build in terms of ints, but we can't have a stack of int primitive types. So we'll just keep things in strings because we know we have our friendly little parse int that can pull numbers out and do our math real quick and then put the numbers back in and all that stuff. So we'll say private stack of string type, and we're going to call this guy our solution stack, something like that. Okay, so these are our fields for our shunting yard object. We haven't given them values yet. At this point, they are just variables waiting to have a value. So we're going to have to initialize them in the constructor. So we'll come down here to our public shunting yard constructor. And this guy is going to take in, actually, he's probably going to take in a string expression as our, so this guy will take in a string expression as a parameter. And we might pass him a couple of other things as well, because we're probably going to want this dude to manage some of our linear layouts and stuff like that for adding and removing crap. But for right now, let's just have him take in the expression stuff. Let's get this kind of working in terms of the logic, and then we'll make our screen catch up. That make sense? All right, so shunting yard is going to originally take in a string, and we actually wrote this logic last time. And then what are we going to do? We're going to parse that string, tokenize that string, and add it to our queue. So before we can do that, we need to make sure that all of our fields here have values. So we're going to go ahead and we're going to say this dot input queue is equal to a new queue. This dot op stack is equal to a new stack of strings. This dot output queue is equal to a new queue. And understand that we are choosing to use our own queue that we wrote here. If we wanted to use Java's built-in queue, we would say new queue of strings like this. And then we would not be using our local Java class called queue. Instead, we'd be using java.util.queue. Does that make sense? So I'm really showing you that this is our class we wrote. This is the one that came with Java. We don't know the quality of that. So certainly our implementation must be better, right? I'm very upset that Van is not here yet, because this coffee is empty. Yeah. It's not going to bode well for your grade. It's just garbage. All right, output queue. Then we'll go ahead and say this dot solution stack is equal to a new stack of strings. And this guy right here, same thing with our stack for op stack. We could have certainly made this a stack of character objects. We could have made this guy a stack of integer objects. We could have made that work. But, we kind of pick strings. This goes all the way back to when we first started talking about Java for this group. That would have been the second half of 200 or last third of 200, something like that. Where I advertise Java as well as C# as being string-based languages. So if you can, strings are very malleable in these languages. If you can get something into the format of a string, you can pretty much do anything you want with it. So using strings for our guys here are pretty safe bet for us. It would probably be more headache to convert stuff to character types or things like that than it would be otherwise. But this is certainly not a requirement. It's just a choice we're making. All right, so now we want to go ahead and we want to do our magic that tokenizes this expression and ultimately puts it into our output queue. So let's go ahead and grab that code from our main activity. So Here's our, when we hit that process button, that's when we go ahead and get the text from this guy. So let's just go ahead and just steal that code for right now. No, let's just write it again. We're going to have to change so much stuff. It'll be a better review just to go through this guy again. So we'll have this guy take in an expression, and we're going to go ahead and we're going to tokenize that expression and add everything to our input queue, kind of ready to go for our shunting yard stuff. Okay, and again, this is our constructor, so that's what constructors are meant to do. They're meant to build an object and kind of prepare whatever you need to prepare for things to happen. So we're going to go ahead, we're going to build a string tokenizer. And we're going to build this string tokenizer in terms of the expression that was passed in, along with the operators that we're tokenizing it on, plus, minus, times, and divide, along with a true. And what, anybody remember what this last true is for? What's that parameter to the constructor for string tokenizer indicate? Yeah, it means give us the delimiters back. Don't just separate on the delimiters, include the delimiters as tokens, because we're going to want those operators. They're kind of an integral part to doing some math. Okay? So then we'll go ahead and say while st.has more tokens, so as long as there's still stuff in our tokenizer, we're going to go ahead and we're going to say this dot input queue dot enqueue st dot next token. Okay, so this should load up our input queue with the values that are there. Okay, now what I'm going to go ahead and do here is, just maybe for the sake of time a little bit, instead of passing an expression in directly here, let's go ahead and give this guy the starting point for the means by which he's going to get that expression. So that came from our input text, right? So back here in main activity, we actually get our expression from input et get text. And input et is our edit text. So we actually want to have this guy as a variable inside of our let's think about this for a second. We want this guy as a variable inside of our shunting yard so we can read stuff in, because we want to have that shunting yard object capable of doing this stuff multiple times. Okay, so we'll go back into shunting yard. I'm going to give myself another variable up here. So we have an edit text called input et, and we're actually going to go ahead and pass that guy in here. So this is going to be a edit text, and we'll say this dot input et is equal to input et. All right. Now, as it goes right now, and what we'll end up having is this dot input dot et dot get text dot toString. That's what we're ultimately going to do. But if we have our shunting yard actually tokenize what's in there the second we create it, then this guy's only good for a one-off. Okay, we can't use him to apply the shunting yard algorithm to different inputs in input et. So instead, I'm going to steal that code, and we're going to give ourselves a function here that just says process expression. Okay, Because what we ultimately want to do is when inside of our main activity, when it, on load, when it first starts, or on create, we'll go ahead and create our instance of shunting yard, passing this guy any of our linear layouts, stuff like that we're going to need. Right now, we're just giving our input box, but we'll pass some more stuff in here. But then when we hit that button on our interface that says go or whatever, okay, and we say we want this to process the expression, at that point, we're going to have it actually read in the current value from our input ET, and then actually process that guy. All right, so we're going to give it a public method here called process expression. And process expression is going to go ahead and tokenize whatever the current value of our input text box is and load it into our input queue. Now, something we want to be careful of, though, if this isn't the first time we've run this, our input queue and the other stuff might have things in it. All right, so we need to make sure we go ahead and empty all of our data structures when we go to do this. All right, so now in our queue, we did not write an empty, right? We don't have a way of emptying our queue. So I'm going to go ahead and we're going to create a public void. Let's call this guy remove all. That will remove everything from the queue. Based on how we wrote this queue, how can we remove all elements? Set front and end to null. This dot front is equal to null. This dot end is equal to null. And then probably this dot count goes to 0, right? Now, let's think about what's actually happening here. Let's say I have 30 things in my queue. Front points to the first thing, end points to the last thing. When I set both of those to null and count to 0, what's actually happening under the hood? Have I actually deleted these objects in the middle, these 30 objects? Yeah, so I've removed the pointer to them, so I've decremented their pointer count to 0, right? Then what happens? How does Java work? Automatic garbage collection. So the little dump truck with the big skull on the side of it, Java's version of Grim Reaper, is going to start coming through memory, looking for abandoned objects and killing them off. Okay? So effectively what we're doing here, if we want to be like morbid about it, is we are marking these guys for death. Okay? We're not going to do the dirty work ourselves. We're just abandoning them in memory and waiting for the dump truck to come through and kill them. Okay? I've told this story before about the conversation I had at it was at a breakfast place with some guys when I used to do system administration work, and we were talking about spawning off child processes and reaping children, and so this is at breakfast, and we're talking about creating new parent objects and spawning children and then reaping the children and all this stuff, and this old couple that was sitting behind us didn't like the conversation. They were taking it completely out of context and kind of like we were planning on some sort of serial child killing thing. It's like, we can kill these children here, no problem. That's an easy one. All right, so our remove all here is leveraging Java's ability to automatically clean up memory, right? Just like, look, we'll just reset our pointers, go back to the beginning, and let Java clean up our mess. All right, same philosophy I have at home when I make a mess. My wife, automatic garbage collection. Okay, so, and we'll see here in a second that our stack data structure that comes with Java has the ability to empty itself. So we'll go ahead and let's go ahead and tell all these guys to empty themselves, even if they're already empty. I mean, we could ask the question, if count is currently 0, don't do anything. Otherwise, do something. But we'll say this dot input queue dot remove all. This dot op stack dot remove all elements is the one that's built in there. This dot output queue dot remove all. And this dot solution stack dot remove all elements. Okay, so what does this guy do? This clears all of our queues and stacks for reuse. Something like that. Is reuse a word? It is now. All right. That makes sense? We want to make sure we empty out the stacks and queues that we're going to be using before we start tokenizing the new version of our input expression. All right. So at the end of process expression, what we're going to go ahead and what we have is we have our queue ready to go. Okay. That guy's ready to start processing some stuff. All right. So what's the next thing that we do? Let's go ahead and I think I mentioned a little bit ago, we're going to kind of do this two separate ways. We'll have a single button click that just does the math, magic. Okay. But what we really like to see is we'd like to see our Android application kind of show us the steps. Something get removed from here and either show up here or show up here. You know, that kind of stuff for our various stacks. And then in the end, we can, you know, so we want to see that thing happen. Okay, rather than it just magically poof, it's done. All right. So what we're going to do is we're going to build little functions for those individual little moves, right? So we might say process maybe input queue, something like that. And that guy's job is to take one element off the input queue, dequeue from the input queue, and then do something with it. Either put it onto the output queue if it's not an operator, or do the operator magic if it is an operator. Okay? So we'll go ahead and say public. I'm gonna actually have this guy for right now, just thinking ahead. I'm gonna have him return a Boolean, whether or not we actually were able to do something for our process input queue. Because we want this guy to return a false if our input queue has nothing there, right? So we wrote our queue. Do we have a way of asking, is this guy empty? Get count, if get count is 0. So we'll say if this dot input queue dot get count is equal to 0, go ahead and return false. We have nothing to do. Okay. Otherwise, let's do our stuff. We have somebody to dequeue and put somewhere. All right. So let's go ahead and dequeue our value. We know that our input queue is filled up with strings. Okay. So let's just give ourselves a variable for holding the string from the front of it. So we'll say string temp is equal to this dot input queue dot dequeue. Oh, this guy actually gives us a node, so then we'll say get payload to get us our string. Make sense? So now I have a string. I just removed the guy from the front of the list, so I have, could be a plus sign, could be a multiplication sign, could be the number 123. I have a string representation of something that used to be at the front of my queue and now has gotten out of line, and I'm ready to process him. Okay? So now I need to ask the question, are you an operator? Okay. If he's an operator, I need to do something special. If he's not an operator, easy mode, right? All right, so I need to ask the question if he's an operator. How can we ask the question, is temp an operator? Lots of different ways we could do this. Anybody have a suggestion? We all wrote this, right? How do we detect whether the string that's currently inside of temp is either a plus sign, a minus sign, a multiplication sign, or a division sign?
index of and char at to see if it was in the string.
That's probably the way I would do it. Okay, so what we can do is we can say if the string plus minus times divide dot index of temp, I'm going to ask if it's equal to -1. So when I look for temp inside of this string, if I do not find it, it's going to give me a -1, correct? Which means that we have a non-operator, or we have a number, okay? i.e. a number. And what do we do with numbers? We enqueue them in the output. So this dot output queue dot enqueue, and this guy takes in a string value. We'll go ahead and give it temp. Easy street, right? Done. All right, else. We're in here. We are looking at an op. And if we're looking at an op, we know this guy's going to ultimately go into our output stack. Or, I'm sorry, our op stack. Okay, we know this guy's going to ultimately go on our op stack. But we might not be able to just throw him on the top right off the bat. We're only allowed to put him on top of the op stack if his value is greater than the value of the guy at the top of the op stack. That makes sense? All right. Now, since we are limiting this to plus minus times divide, we know we're allowed to add this guy on top as long as he is, if we have a minus sign, as long as it's not well, actually, let's see. Given those four, we would only ever add something directly if whatever's on top, if we're trying to add a multiplication or a division on top of anything. So if it's multiplication or division, we're allowed to, well, no, not necessarily allowed to just directly add it because you might have division on top. Yeah, you can always do it if it's plus or minus. So I think the cleanest way of doing this is going to give us, maybe write a little private method that gives us a value associated with a particular operator. And we know that we happen to have our operator in string format. So we'll run out to Home Depot real quick, write a little function that we can pass an operator to, a string representation of an operator to, and it will give me back a numeric value for it. Okay? So we'll come down right here. And what I'm going to do, just so I don't forget, here at the end of this else, I'm just going to do a return true. We know we're going to ultimately process this guy. So if I had nothing to process, return false, process input queue didn't do anything. Otherwise, we'll do our stuff that we're in the process of writing right now. And then at the end, we'll go ahead and, yeah, I did my stuff. Return true, I made a move. Okay? So we'll come down here. And we'll make this function private because he's only needed inside of our shunting yard .java class, right? Okay, so we're going to say private int value for op. This guy will take in a string op as a parameter. And we can kind of just randomly choose the values we want as long as plus and minus are less than multiplication and divide, right? So we can say something like if temp dot equals, oh, I'm sorry, not temp, if op dot equals the string plus or op dot equals the string minus, maybe return a 0, else return a 1. Multiplication, division would be 1. Plus or minus would be 0. That should give us numbers to do greater than stuff with. Make sense? Okay. So that's our value for op. So let's go ahead and if we have an op, let's get int val for op is equal to this dot value for op of temp. So now we know the numeric value for the operator we're trying to add. Okay? And we want to try to add him to the top of the stack, but as long as the top of the stack has a value that is less than or equal to val for op, we need to pop it and put it onto our output queue. That is to say, we're only allowed to push temp onto our op stack if it is greater than the thing that's currently at the top of the stack. All right, so we'll go ahead and ask the question. Actually, let's ask the question. We don't even care what the value is if the stack is empty, right? So if this dot op stack dot is empty, we're free to push it. We'll say this dot op stack. I hate this keyboard. Op stack dot push temp. Else, we know there's some stuff in there. So we're going to go ahead and get our val for op. And then we'll say while this dot op stack dot is not empty. So I put the not in front while this dot op stack not is empty. Okay, you can also say if is empty is equal to false. That says the same thing. If you like that version of it better, this is just redundant, but it might look cleaner to you. So when I ask if the op stack is empty, if I get the answer of false, meaning there's stuff in there, and the stuff at the top has a value that is less than or equal to val for op, then I need to remove it and put it onto my op stack. So, and this dot op stack, I'll go ahead and grab peak, and this gives me that string. Now I'm going to use this string to get the value for that operator. If that guy is less than or equal to val for op, then we do some stuff. So as long as our stack is not empty, as long as there's something there, and the current top of the stack has a value that is less than or equal to the value I'm trying to add, then I need to go ahead and say this dot output queue dot enqueue this dot op stack dot pop. So pop it off the op stack and queue it into the output queue. Loop back up, ask the question again. Is the op stack empty? Is the guy currently at the top less than or equal to the guy I'm trying to add? If yes, do that same thing again. As soon as we clear this while loop, we know that the op stack is ready to receive temp. For whatever reason. It might be that it's empty. We've cleared it out. It might be that we are now allowed to put something on top for legal reasons because the guy we're trying to add is greater than the guy that's currently on top. So we can go ahead and say this dot op stack dot push temp. That makes sense? All right. Now, whenever we push something into our op stack, visually we want to see that happen on our screen, correct? So we need to make sure we do our logic in here for those movements, right? So what I'm going to do right now, let's go ahead and give ourselves, have we actually written our Do we give ourselves layouts for those different things? Let's go check here. So we have our input, we have our button to parse stuff, we have our output text view. So that's just the guy that's doing our. So we need our output queue, our input queue. Show us that guy. Then we need our output queue, and we need our op stack, and then we need our solution stack. So we can see those individual steps. So let's go ahead and put those on our screen. So I'm going to alternate between labels and, well, actually it'd be labels and labels, right? Because they don't need to be editable, but I'm going to have a label that will label what this guy is and then whatever. Okay, and just for screen real estate reasons, we'll just put them right on top of each other. Okay, so we'll go ahead. This is a new palette, right? So right above that guy, we'll go ahead and say input queue. And let's change this guy's name to input queue. And I'm going to copy those. And then what just happened? Well, I did that as an edit text. I thought that was. All right, so that guy must not be. There's our text view. It was a little bit misleading. That's pretty good. Bold that. Okay. Ay. So that's the text view. That's that guy. So I'm going to go ahead and steal this guy. We'll paste him. Drop him here. So we'll call this guy our op stack. Steal this guy. Paste him. This will be our op stack. And actually what we want to do here, because our input queue and our op stack, well, actually all those guys, because they work like stacks or queues, rather than treat them as labels, we'd probably be better off treating these guys as linear layouts and then building labels to throw in there. Okay? So let's dump this. Let's just give our other labels here while we're at it. So we have input queue, we have op stack, we have output queue. And then we have solution stack. Oh. Well, I'm going to actually change it to that. All right, so those are our labels that will label those different things, right? Now what I want to do is underneath each of those, I want to give myself a horizontal linear layout. Something we can add and remove stuff to for representing our shunting yard. Make some sense? So we'll come up here to our layouts. And here is our, that's interesting. This picture looks like a vertical linear layout, does it not? This one right here. And this one looks like a horizontal linear layout. Why are they backwards here? Who do they have there writing this code? Must be freaking 300 students. 200 students. Okay, so let's see which is real. So I'm going to go by picture, not by this text. So we're going to go ahead and give ourselves a horizontal linear layout. And I'll drop it after this guy. And what did I get? No, I got a vertical. So go back to horizontal linear layout. And we will have the height wrap content. Okay. And we're going to go ahead and give this guy a name. So this guy is going to be our input queue linear layout, right? So that's our input queue. And then I'm going to go ahead and steal that guy. And now this guy is going to be our op stack. Really, that's like a fun word to say, op stack. Okay, then we have it didn't have that guy wrap content. So with wrap content, if there's nothing in there, it'll squeeze down, which might make our interface look a little funny because initially it won't be anything there. As soon as we do something, our interface will expand a little bit, but it's fine. All right, then this is weird. If I copy something, shouldn't it take the properties with it? You would think, yeah, you would. It's garbage. All right, so this is going to be our output queue. All right, here we're gonna try this. I'm gonna copy that one. We're gonna paste that one, and this is our So I must have copied it maybe before, or possibly not, based on some of the other things we see with the Android Studio. It's possible it just picks and chooses whether to copy the properties or not. So this guy's going to be our solution stack. Okay, so now I have my linear layouts for holding my output, and then some labels for this guy. Wait, hold on a second. No, I clicked on the. Oh no, it didn't. It didn't keep it. Yeah, I selected the wrong thing. This was the guy I just pasted. And this guy is our solution stack there. I need to turn this guy back into text view 7, I guess. Just something that's unique. There's our solution stack. Yeah, it did not do the other thing. Okay. Fair enough. So now we have access to those guys. So let's go ahead and give ourselves programmatic access to them. So this is going to be inside of our main activity. So we're going to go ahead and get rid of our output text view. And instead we're going to have a view that is going to be, this is going to be what? Input, input queue, private view, op stack, private view, output queue, private view solution stack. Okay, so we no longer have this output guy there, but let's go ahead and hook up our 4 linear layouts here. Actually, are we able, can we say this? Can we say linear layout? And I think it should be just a generic view. Yeah, I'm pretty sure it's a generic view. Okay, so let's go ahead and we'll hook these guys up. So this dot input queue is equal to the view version of this dot find view by ID r dot ID dot input queue. This dot opstack is equal to the view version of this dot find view by ID r dot ID dot opstack. This dot output queue is equal to the view version of this dot find view by ID r dot ID dot output queue. This dot solution stack is equal to the view version of this dot find view by ID r dot ID dot solution stack. All right, so we have all those guys hooked up. Now let's go ahead and pass those guys into our shunting yard algorithm. So I'm going to go ahead and give ourselves a private shunting yard SY up here. And before we go any farther, let's go into shunting yard. And we're going to take in a little bit more in our constructor than our edit text that we're currently taking. We're going to go ahead and take in our views that represent all those other things. Okay, so up top here, and I'm actually going to steal it from here. So there's all the views that I need. Oh, let's throw a, we'll just throw the word view at the end of all those, since we also named our data structures input queue and all that. All right, there we go. So this is going to be a view input queue view, view opstack view, view output queue view, view solution stack view. And then this dot input queue view is equal to input queue view. This dot opstack view is equal to opstack view. This dot output queue view is equal to output queue view. This dot solution stack view is equal to solution stack view. All right, so now we have access to all of those various views. Okay. So down here, when we process our expression, and we go ahead and we enqueue stuff into our input queue, which means put it at the end of the line, right? We also then want to create a label with that particular guy as the text and add that to our input queue view. So what we're going to do right here is we're going to say string text. We'll say text is equal to st.nextToken. So we'll go ahead and preserve that, because remember, st.nextToken burns the token. It's gone. And I actually need to use the string from it twice. I'm going to use it to add the string to my input queue, or my output queue, right? Input queue. Okay, I'm going to use the string for my input queue, but then I'm also going to use the string to build a label to add to my input queue view. Does that make sense? So we'll go ahead and add our text here. And then we'll say this dot input Q view dot was it insert? What's my what's the function for adding something to a view? Oh, view group, that's right. I always do that, don't I? Okay, there we go. And then these guys need to take in view groups. Okay, so now we should be able to add a view. And let's see, for a linear layout, I think adding view should always add it to the end. So I think it'll already act as an NQ. Let's check to see if that's the case. And we're going to add a new label. Well, it's actually not a label, it's a text view. Does this let me set the text in it in the constructor? Nope. Oh, why did I call it a string? All right, so we'll go ahead and create a new text view. So does it, is there one that lets me? Oh, it wants the context. So I'm going to need to give myself the context of my main activity. I don't think I can give it a null context. Just say private, that guy, context, and we'll just get it to a stopping point here in a second. So app compatibility context, we create this guy, we'll pass it our this dot context, and then we'll go ahead and add that view. We need to make sure we pass our context in with this guy, so that's this guy context. This dot context is equal to context. And then back in here, when we build it, final step here, we'll say this dot sy is equal to a new shunting yard, and this guy takes a whole bunch of stuff. We're going to give it our input Q. Actually, we got to give it our input ET, our input Q, our op stack, our output Q, our solution stack, and then finally us for the context. So now that shunting yard algorithm should do all that stuff. And then down here, we'll say sy dot process expression, which should then populate our output Q. Because this guy on process expression, when we hit that button, is going to empty out all of our Qs, do our tokenizer, split everything up, but each time through, it'll enqueue it into the actual queue, but then it'll also add a text view to our input Q view. All right. So I'll go ahead and push this to GitHub, but let me look at our book here real quick. Just want to see where we're at for where we're going. 300. Stacks queues. They're good there. Go ahead and let's read chapter 3 on hash tables for next class. We're probably not going to do a ton of stuff with hash tables. I'll probably try to do something in the next assignment with it, but it's a good thing to, some other languages are called dictionaries. Okay, so chapter 3 on hash tables for Thursday. And then we'll finish this up. Oh, don't forget, we got student, faculty, staff Bible study today. Free lunch, Scott and Grub. You going today?
Yeah, I promised you I would.
I know. I was going to see if you're going to break that promise. I figured there would be an excuse. That we're meeting in 7 minutes down there?
Yeah, I just had to turn my phone charger.
That's fine. I'll see you down there. Code from 32817.
So when we cleared out the queue,
Yep.
you're changing all the pointers and stuff, was that kind of what you were talking about yesterday when I was talking about the items? Because you said after you use the item.
Yeah, you just kept tacking stuff onto the end of it. You never actually cleared it out.
What about that for the game?
Yeah. No, I know.
Oh, I thought
Yeah,
you were talking about for the.
Yeah, no, it was very similar. Yeah, for you, every single time you called that function, you kept tacking stuff onto the end of something that already had crap in it.
Oh, I'm not the prime thing.
Oh, okay.
The other one. We were talking about the treasure chest and the items and stuff.
Oh,
You were
well,
saying
that one's different.
each time-
Yeah, because that one is if you hand somebody a potion from this treasure chest,
Yeah.
and you only created an instance of that potion once,
Yeah.
and they go and drink that potion, now the potion because the potion that's in their treasure chest and the potion we hand to the guy is the same memory address. They both point to the same place.
Okay.
And now that dude drank this potion, so now the potion in memory is empty. So the next time you hand out a potion from the treasure chest, it's empty. Yeah.
So if I destroy both of them and make a new instance of the
You
treasure-
probably, I don't think you need to destroy both of them. I think what you'd want to do is if they randomly select potion, the potion from the chest,
Yeah.
which you would return to them as a new potion. You would create a new instance of it and just leave this guy alone.
Okay.
So
Okay.
always on the shelf, we have a full potion that was an instance of a potion that's never been touched.
Okay.
And then we always hand you new instances.
Okay.
So this guy's never impacted.
So they're both kind of the pointer issue, both things. Like
Yeah, this guy will then point to his own place, and this guy's a brand new memory address because we just created an instance of it.
Yeah. Pointers are kind of not much.
Well, it's supposed to be a little confusing now. That's why